Hi, good evening everybody. In these sessions, let us discuss, the DFT session 4 actually DSP topic. Session 4 this is. In these sessions, let us discuss reconstructions of original signals from frequency domain samples. Right, this topic is coming under DSP, under DFT module, first module, right, which is coming under VTU Module 1, 5th semester students, right? Myself is a professor in EC department, belongs to Cambridge Institute of Technology, Bangalore. Now, in all my previous videos, in my previous video number 3, we discussed how to get frequency samples from the original signals for a time domain signals, right? And we told you what is the benefits and all. To process, to analyze signals we have done. But in the end, we want original signals back. Original signals back. For example, you are calling your friend and saying that I am so and so here. At the receiver, right, it is changed. Here at the transmitter, you are changing all these things, frequency domain, digital, discrete, send, all that done. In the end, at the receiver, you want original signal. I am so and so only back. Then what I will do? Let us see the derivations, how to get reconstructions of original signal XP of n from the sampled signals, from the samples, frequency samples. Again, in these derivations, only two expressions, discrete Fourier series expressions. Again, great man there is, right? This standard expressions, if you consider two expressions, it is easy, right? We can reconstruct original signals. Let us see how. We know that XP of n is a periodic signals with a period of n samples, right? In my previous sessions we have seen. Then it is expressed by using DFS by the following standard relations. How to get original signal E? XP of n, periodic signals using DFS, discrete time Fourier coefficients, discrete Fourier series. We can get original signal XP of n using this expression, standard, derived. X of summations k is equal to 0 to n minus 1, C of k, Fourier coefficient, C of k is nothing but, into e power plus j 2 pi k by n into n. This is a standard expression. Call this equation number 1. To get back original using DFS, using Fourier coefficients. But here where C of k is nothing but, if you remember these expressions, later you change this plus as minus. C of k is nothing but Fourier coefficients expressed by other standard relations like this. C of k is equal to 1 by n, number of samples, into summations n is equal to 0 to n minus 1. Instead of k is equal to 0 to n minus 1, n is equal to 0 to n minus 1. N is equal to 0 to n minus 1. XP of n is original signals. This original signal. XP of n, C of k obtained in terms of XP of n. That's what. XP of n into e power plus j, here plus j, here C of k is minus, that's all. Rest is same. E power minus j 2 pi k by n into n. Call this as equation number 2, where k is equal to 0, you get 0, 2, 3, like that you will get. This is second discrete Fourier series standard equations derived, given by the great man. Now, I want this C of k is there, Fourier coefficient in terms of frequency samples, frequency domain samples. This C of k in terms of frequency domain samples I want. Then what I will do? I have already derived. In my frequency sample derivations, first derivations, last video we have shown that. According to equations derived for spectrum sampling, frequency samples, we get this. We have done this. X of 2 pi by nk, frequency domain samples, is equal to summations n is equal to 0 to n minus 1, n number of samples, xp of n, e power minus j 2 pi by nkn, standard relations. This we have derived in the last sessions, right? The frequency domain samples for the signals, right? This let me write for C of k. Let me explain Fourier coefficients in terms of the samples, frequency samples. That's what I do. For example, see these equations. Fourier coefficients C of k is nothing but 1 by n. 1 by n into whole thing. This is nothing but this only. X of 2 pi, this whole thing is there, no? N is equal to 0 to n minus 1 hp of n equals minus a 2 pi k n by n, which is this one. N is equal to 0 to n minus 1 hp of n equals minus a 2 pi k n by n. Substitute here in place frequency domain samples. Because we know this standard equation. Then your C of k becomes C of k is equal to 1 by n into x of 2 pi by n k. That means Fourier coefficient C of k is expressed in terms of samples, frequency domain samples. That's what I do. Therefore, substitute that into C of k, we'll get C of k is equal to 1 by n into frequency domain sample. Whole thing is nothing but x of 2 pi by n into k. Call this as equation number 3. That means your coefficients, Fourier coefficients is expressed in terms of frequency samples. This is what I need. This let me substitute into main equations of number 1. Periodic, what is it? Original signals we are getting. Right, using that this equation is there now. Right, this equation is there now. Original sequence xp of n, reconstructions. Using this DFS is there now. Here, in terms of frequency samples I want. C of k in terms of frequency samples I have got. Substitute the C of k from that samples. What will get? See, for example, I know this C of k is equal to in terms of samples. Substitute these equations into equations into equation number 1. This into equation 1. We get original sequence in terms of samples like this. xp of n is equal to 1 by n. Summations k is equal to 0 to n minus 1 is that. Summations k is equal to 0 to n minus 1 is there. What is C of k? C of k is nothing but 1 by n into x of 2 pi. See, C of k is equal to 1 by n into x of 2 pi by n k, no? That I am substituting 1 by n x of 2 pi by n k, right, into e power plus j 2 pi k n by n is there. Therefore, this is what reconstructions. Finally, we get reconstructions of original signals from the frequency samples. See that xp of n is equal to is discussed or expressed. Xp of n is obtained, original sequence is obtained from the samples. Frequency sample x of 2 pi by nk, which we have got already, right? That means original sequence is obtained from the frequency domain samples, right? This is the standard equations. This is the standard equations. This is also called as IDFT equations, right? That is DFT equations. This is IDFT. That means DFT equations is equations where we are expressing frequency domain representations for the time domain signal x of n. After processing, sending, everything, we want original value. The reconstructions, original signal is obtained from the process samples. Is this right? That's all, right? Let me quickly revise today's topic. What is that? Reconstructions of original signals from the samples. We know the standard original signals, periodic signals, right? Using DFSS by these equations. Xp of n is equal to summation k is equal to 0 to n minus 1 C of k into e power plus j 2 pi k n by n. Call this equation number 1. C of k is nothing but Fourier coefficient. Express this using one more relations, that is 1 by n into summation n is equal to 0 to n minus 1 xp of n into e power minus j 2 pi k n by n. Then according to we know this, according to spectrum sampling equations, we know this frequency samples is equal to in terms of periodic signals is this. Then substitute this here in C of k. You will get C of k in terms of samples, Fourier coefficients in terms of frequency samples. You substitute this into main equations. You will get original signals in terms of frequency samples. This is also called as IDFT equations, right? Therefore, that's all. Using these equations, you can get original signals xp of n from the frequency samples. I hope I am clear. Right, this is how to get original signals from the samples and also the samples from the original signals. Next class, let us see, right, all these problems, beautiful problems we can solve using these two equations. That is more interesting, right? We'll do that tomorrow, maybe next class. Thank you.